Every element has a characteristic atomic mass because they each have a different number of protons, neutrons, and electrons. Most of the time, you won't use the actual masses of each element's atoms. Subatomic particles are so tiny, their masses are so small, that it would make problem-solving unwieldy. For instance, the mass of a proton is 1.67 times 10 to the negative 24 grams. The mass of a neutron is 1.68 times 10 to the negative 24 grams. And the mass of an electron is 9.11 times 10 to the negative 28 grams. Adding and multiplying numbers of those very small sizes is awkward. So instead of using the actual mass of atoms in problems, chemists compare all atoms to one standard atom. They picked carbon-12 as the standard. Carbon-12 is the isotope of carbon with 6 protons and 6 neutrons. Carbon-12 is assigned a mass of exactly 12 unified atomic mass units, or U. Some people write AMU, or Daltons. Chemists just defined a new unit for convenience. See, it's much easier to think and write that carbon has a mass of 12U than to add up all the small masses of all of its protons and neutrons and electrons and write 2 times 10 to the negative 23 grams. It's just a lot easier to think in terms of whole numbers. So then, helium is about 4U, because a helium atom is about 1/3 the mass of a carbon atom. 12U divided by 3 equals 4U. Hydrogen, the smallest atom, is about 1U, because it's about 1/12 the size of a carbon atom. 12U divided by 12 equals 1U. So why, when you look at the periodic table, does it not say exactly 12 for carbon's atomic mass? Because there is more than one kind of carbon. Remember, chemists assigned carbon-12 the mass of 12U. But there are other isotopes of carbon. Carbon-13, which has 6 protons and 7 neutrons, and carbon-14, which has 6 protons and 8 neutrons. If you need a quick refresher on isotopes, please watch our short 30-second glossary video. Carbon-12 and carbon-13 are stable, but carbon-14 is radioactive, so it is slowly decaying. Maybe you've heard of carbon-14 dating of fossils, but that's a topic for another video. On Earth, there's a lot of carbon-12, a little bit of carbon-13, and a very small amount of carbon-14. To find the average atomic mass of carbon, you take a weighted average of these isotopes based on their natural percent abundances. First, let's make a table of the isotopes, their masses, and their percent abundances. I would look these up. This isn't something you would know off the top of your head. The amount of carbon-14 is so small, it's less than 1,000th of 1% of the carbon present on Earth. So it won't play a part in our weighted average. It's just not significant enough to affect the mass if we go to 2 decimal places. When we measure and then round to 2 decimal places, notice that the percentages of carbon-12 and carbon-13 add to 100%. So we know we're okay disregarding the very small percentage of carbon-14. Change the percent abundances to decimal fractions by dividing by 100%. 98.89% becomes 0.9889, and 1.11% becomes 0.0111. Check your answer. There are 2 types of carbon we're worried about here. Let's call them A and B. A weighted average will be decimal fraction A times mass A plus decimal fraction B times mass B. That's 12 times 0.9889 plus 13 times 0.0111, which equals 12.0111, or about 12.01 unified atomic mass units. That should be close to what you see on your periodic table. Does this answer make sense to you? Remember, most of the carbon on Earth is carbon-12, and only a little bit of it is carbon-13, so the weighted average should be really close to the atomic mass of carbon-12. And it is, just a tiny bit more than 12U, due to the little bit of carbon-13 which is heavier. Let's do one more example. What is the average atomic mass of oxygen? Here's a table of the isotopes of oxygen with their masses and their natural percent abundances. The weighted average of the three isotopes, let's call them A, B, and C, will be decimal fraction A times mass A plus decimal fraction B times mass B plus decimal fraction C times mass C. Convert the percentages to decimal fractions by dividing by 100%. 0.9976, 0.0004, 0.002. The weighted average is 16 times 0.9976 plus 17 times 0.0004 plus 18 times 0.002. That equals 16.0044, or approximately 16.00 unified atomic mass units. You may get a slightly different answer depending on how many decimal places you have in your percent abundances measurement. Check your answer to see if it passes the smell test. You know that the most common isotope by far is oxygen-16, so the average atomic mass should be really close to 16U. And it is.